With this configuration, we hope to differentiate the input over time and also multiply it by a factor of k, which we hope to be more than 1. We want to amplify the input and also differentiate it, hopefully for some useful frequencies. Now, before we do anything here, we note that this configuration is a more general case of this configuration, with the impedance between the input and the inverting input of the op-amp and an impedance between the inverting input of the op-amp with the output. We are going to study this case for now, and we are going to go here later just so we can see some things here. The voltage here at the inverting input must be equal to the voltage here. Why? Because this is grounded and we have an ideal op-amp and we have a negative feedback configuration. I'll name this node point X. I'll say the voltage here must be 0. This is known as a virtual ground because the voltage here is always 0, and this is important. No current leaks to the ground from here. There is a common current flowing from the input going all the way to here and then going upwards. It doesn't really flow inside the input since we have an ideal op-amp. And we take the impedance law now for this impedance and this impedance. This is similar to Ohm's law, and we say that Z1 must be equal to V in minus Vx. Alright, let me draw the polarities here. V in minus Vx over I. Vx must be 0, obviously. And then we calculate the impedance here, which is Vx minus V out. Again, these are the polarities. Vx minus V out over I. If the polarities were reversed, things would not work as expected. We don't study these cases. The voltage now here must be 0, and therefore I can say that this current and this current are the same. Alright, I say it here. Therefore I can say that V in over Z1 must be equal to minus V out over Z2. And this is my beautiful equation for the inverting op-amp configuration, the more general case. This is very, very useful, and we are going to use this to simplify our analysis later on. Now, I can go ahead and go in my original circuit that I cooked up, and I can say that this is Z1 and this is Z2, and I can simply say that V out over V in is the impedance of the resistor over the impedance of the capacitor with a minus sign in front. This is very good way to approach this instead of doing KVLs and KCLs here with a varying current which depends on the voltage of this capacitor and doing complex things like this. This is a very practical way to approach this. Now, I replace the impedances here. Vs is the j omega, obviously, the speed of the input signal, and this is the Laplace form of the signal. I'll prepare a Laplace video later on. If you really wanted to, type me in the comments below. Now, V out over V in, if we do the math here, must be equal to minus S over 1 over R2 C1. This is going to help us a lot now because we can say that, well, if I put the input signal here, I can perform the inverse Laplace operation, which is nothing but the differentiation of the input over time multiplied by a constant value here. And that's it. That's pretty much it. We seem to have something that works, alright. The output is a differentiation of the input multiplied by a value here. Alright, obviously there is a minus sign here. Doesn't mean anything. It just means that the output signal is going to be inverse in respect to whatever differentiates the inputs. Alright, no problem. And now let's draw a ladder function for the inputs. Alright, something like this. And I can predict that the output is going to look like this. Alright? This tool, alright, seems to have something, we seem that we have something that works. And now let's study how this responds to the change in frequency. So if we plot V out over V in, and we use this equation now, alright, respect to the frequency, we will note that as long as the frequency rises, the output over the input also rises, alright? You see the linear relationship here. Obviously, this is the absolute value here, alright? And it goes on and on and on like this. This is a high-pass amplifier or high-pass filter. We call it amplifier because we amplified by a value here. And we note that, well, my useful signal is going to be between some kind of range here, all right? And there are going to be some other signals. They can be higher than my useful signal, much higher, orders of magnitude, that are going to be probably noise, all right? And these signals are going to be amplified, as you see here, are going to be differentiated, all right? Which we don't really care. But what we care about is that they're going to be amplified by a higher factor than my useful signals here. So as long as they get amplified with a higher factor here, I'm going to have a problem, because at my output, if I go to measure the output, I'm going to measure so much noise here than signal to noise rate. My signal to noise ratio is going to be much smaller here. This is a problem in other classes. You're going to study this in more detail, but for now, let's keep our understanding in this confinement of this graph. And it turns out that even if we try to fix this, all right, usually we don't use differentiators that much in our integrated circuits. Instead, we try to use integrators more, which are more stable and somehow cheaper to make and easier. All right, I have an integrator video in this channel. You can check it out. All right. So let's say now that we have to use differentiator. There's no other way. Well, we have to fix this issue now. So what I'm going to do, I'm going to plug in resistor between the input and the capacitor here. Why? I just want to see what happens. Well, this is now my Z1, which is the resistor in series with a capacitor here. And I can transform my general equation. You see, now that is useful. I don't need to do complex things here, just replace things here. ZR2 over ZR1 plus ZC1. I know the impedances, and if I do the math here, I get this equation. The output over the input is this thing here. Let me note some things here. Well, first of all, I notice that, well, if the R2C1 over R1 over R2C1 is much smaller than 1 over C1 R1, I know that this frequency, as it starts from 0 and increases, is going to get it's going to get closer to this value much quicker than it will get to this value. Therefore, I note that when this is close to this value is very tiny in respect to this. Therefore, this whole thing is 0. Therefore, at the earlier stages of my frequency response, I will note that this value is closer to this, all right? And the output is a typical integration of the differentiation of the input, all right? The previous equations we had before. So this is like we don't have anything here. So this will start from 0. It's going to go up and up and up until a point where this whole thing is going to give us 1. When it is going to give us 1? When the frequency is equal to 1 over R2C1, or the speed, all right, more correctly. Now the output over the input is going to be 1. Why is this point important? It's important because, as we said in the beginning, we want to amplify the differentiated input, all right? We want an amplification at the output. So this point is important because below this, we don't really have an amplification. Now it gets amplified, and this part of the equation holds true up until a point where this frequency becomes big enough to be close to this frequency. And then when these two are comparable, this frequency reaches a point where it is much higher than this. What we call the pole of the function. All right, if you're not familiar with body diagrams, don't worry about it. But practically, what this tells me is that when this frequency gets very close to this and higher than this, all right, if you do the math here, if I multiply this from here, here, and here, all right, if I do some observations, that the frequency here, it turns out to be so much higher than this, that this term being here, so if we draw it like this, 1 over R1C1, 1 over R1C1, all right, we multiply this and divide by this here. It turns out that this is much higher than this. Therefore, it overwhelms this term, but it's also, the whole thing is also multiplied by 1 over R1C1. Therefore, we have a frequency which cancels out with this frequency. This C1 cancels out with this C1. And in the end, we have R2 over R1 with a minus sign here, which tells me that the output over the input is constant in respect to the change in frequency. From a point onwards, not always, this is an area where we have some intermediate situation. But in the end of the day, it's going to look like this. All right? Just to be sure, we say that these things happen with a range of 10 times these frequencies here. So we say that this behavior is true when the frequency here is 10 times higher than this, or the frequency here is 10 times lower than this, right? Same with this frequency, okay, just for safety reasons. Now what we managed to create here is a better high-pass amplifier. Why? Because we have a very constant output over input here in high frequencies. So we have a high-pass amplifier that we wanted to create, all right? And it's also an amplifier. So we have an amplified input. And also, we don't have integration here. No integration, differentiation. All right? And we have a differentiation. This is the bandwidth, all right? Starts from here, it goes up to infinity. Theoretically speaking, in reality, the the op-amp is going to have some kinds of speed that it responds to. In higher frequencies, it doesn't really respond well, but we are talking about the ideal op-amp here. This is not the integrating ability that stops, it's the differentiating ability that stops. This differentiating ability that stops, it stops here, which means that my little configuration, it differentiates from here all the way to here. It also amplifies from here to here and now not here, so okay. But the important thing is that differentiation stops here. All right. We managed to cap the amplification of the high frequencies. This is very important. That's what we wanted from the beginning, all right? And we protect our output signal from being too noisy, all right? We can eliminate this anyway. We can eliminate this completely by adding some extra capacitors here and doing something like that. But let's ignore this for now. Let's say that we have a high pass amplifier, all right, for high frequencies, and we have a typical differentiator from the lower frequencies. Again, these circuits are not really used widely, but it's good for us to understand these things. Now let's look at this exercise very quickly. We are asked to find the first of all, the cutoff frequency of this configuration with these resistances and this capacitance. And well, first of all, what is the cutoff frequency? The cutoff frequency is this frequency here, the frequency we found to where we have the high pass filter, where the filtering starts. All right, the S cutoff is going to be 1 over C1R1. S, as we said, is 2 pi f. Why? Because it's the speed, actually. So the cutoff frequency is 1 over 2 pi C1R1. And if I do the math here, it's about 160 kilohertz. Now I'm asked to find what is the bandwidth of the device. The bandwidth is going to be, obviously I use a negative sign here too, all right, because it's the frequency here and also here, all right, and these are symmetrical. The bandwidth of we're using the same logic is going to be from 160 to infinity kilohertz and minus 160 to minus infinity kilohertz. Obviously, this is an ideal op-amp. The normal op-amp is not going to have an infinite speed. Also, a non-ideal op-amp is not going to have the voltage here being the same as here. It's going to have some leaking currents. All right, this is not a non-ideal op-amp study. This is studying an ideal op-amp with this configuration. So this is done, and I'm asked to find now the differentiation range. Well, as we said earlier, the differentiation range is going to be between here and here. I'll name this point L, right? I'm going to say that SL is going to be equal to 1 over R2C1. This is the point where, if you remember, V out over V in is going to be equal to 1, the point from where we have an amplification of the inputs. Now, FL is going to be 1 over 2 pi R2C1, which is going to be equal to about plus or minus 160 hertz. Therefore, my differentiation range is going to be between here and here, 160 to 160 kilohertz, 160 hertz to kilohertz. All right, plus or minus going to be this and also this in the negative frequencies. Now this is done, and I'm asked now to draw the output if the input has this value. Well, first of all, I notice that the input is a periodic signal, which has a frequency of 10 to the power of 7. Well, because the frequency is much higher than this frequency, all right, I know that I am in the amplification range here. The amplification range, and I remember that the output over the input is going to be R2 over R1. All right. It's always going to be R2 over 1 minus with a minus in front. Again, you can do the math here yourself and find out that this holds true in very, very high frequencies. All right. This term overwhelmed this, and this is going to be simplified with this. The frequency, the capacitors become simplified, and we have 1 shot over 1, which, by the way, is the typical inverting op-amp configuration without the capacitor here. So if we didn't have the capacitor here, it's going to be there are 1 here, and there are R2 between here and here. Now the output is going to be 10 to the 3, all right, 10 to the power of 3 with a minus in front over the input. Therefore, if I draw the input signal here in respect to time, and these squiggly lines just mean that there's a much bigger distance between here and here, all right, 5 to 5 to the power of 3. Don't be confused if you see this in your academic books. It would mean that I have the same signal here, a sinusoid, but with a minus sign and of much higher amplitude. I note an amplification here as I expected. All right. Now let's draw this signal. Well, for this I note that my frequency here is between this range. All right, it's well within the range, so red is not very close to the borderline situations. This tells me that now I can use this equation. Why? Because this term is much smaller than this. All right. Therefore, this whole thing becomes 0. And I can now say that the other bin is minus R2C1S, all right? And if I perform the inverse Laplace operation, I'm going to have that the output signal is going to be this constant value times the differentiated input over time. Well, I know that the sinusoid is going to become a cosine, all right, multiplied by the value here, which multiplies by t. 2 pi tends to the power of 4 times the thing we had here in front. And if I do the math here, my output is going to look like minus 63 times cosine of the initial signal. We got a t here, which means that the output is going to be an amplified version of the input. My configuration works, all right. Oh, thank God. Going to look like this. So we would have an actual cosine here, but we inverse the sign starting from minus 63 up to 63 instead of the opposite. All right, the very typical stuff here. If you want to digest this, pause the video, watch these sections again. Sometimes my students have trouble with this. They want to have these things multiple times explained. So I will understand if you want to watch these sections of the video 2 or 3 times. All right, going to 3, we have what we call a step function. All right, 2 step functions, which create something of a square. It goes like this. Now, if you remember from signals and systems, if you have taken this class yet, if you haven't taken it, don't worry about this section of the video. This is the delta Dirac function, all right? The differentiation of the step function is a delta Dirac function, which has a minus sign in front. Therefore, it's going to look like this. All right, it has a minus sign because this whole thing has a minus sign. Now the output is going to look something like this. Obviously, if we go and try to measure the output with an oscillator, we're going to note that it's going to look, we're going to measure some kind of this sine here, and it's going to be like this signal here. So it's going to be a spike, let's say, of a relatively high value, not very predictable to be honest, and it's going to lower into 0. And then we're going to notice another spike here. All right, and that's it. That's pretty much the op-amp working as a differentiator. Again, this can expand into many other applications. I can also have a capacitor here connected in parallel to this resistor, many things. But these are the basics. If you have any questions, write me down in the comments below. Subscribe for more electronics videos so you can pass your exams very efficiently. Study well and take care.